Good afternoon, everybody. I hope you can hear me at the back. If you cannot, please move a little bit forward. I'll try to be as loud as possible. Normally, that is not my weak point. The weak points are going to come in a few slides, I think, and I hope you spot them. Okay, so I am absolutely thrilled to be back here. I know some of you, and it's so great to see you again. I was so delighted that I didn't have to worry about choosing an appropriate title. Renato is always perfect when it comes to that. And I heard from some colleagues that they're also happy with him, so he's on a roll, actually. I don't see him here, so I don't know, maybe he got bored of me showing him the same slides. I promise you I have some new slides and some exciting results. I hope you'll appreciate. So just to fill you in terms of my coordinate, about 6 months ago, I decided to move to University College London. And for those of you who are students, master's students in particular, I am looking for students. Okay? So I just had to throw it out there. So let's come back to what I want to tell you about, which is going a little bit far, maybe to the other extreme, from the vortices on Jupiter. I'm going to go as small as I possibly can. Okay? So let's talk about nanostructured surfaces. And if we go by what we have heard through eminent speakers throughout the day today, the two most difficult problems that are outstanding in fluid mechanics, or in particular aerodynamics, one of them is turbulence and the other one is icing. I hope we can start to become a little more optimistic about the icing problem. It's hard, but it's not unbeatable. I think we can get there. Okay, so I need to start by showing you my partners in crime. Most of what I'll show you today was actually done in ETH Zurich with my mentor here, Professor Poulikakos. Mainly heat transfer person, but he was nice enough to let me try some of my own fancy while I was there. And first and foremost, the thanks goes to these gentlemen here, the PhD students, who were unfortunate enough to have to be saddled up with my ideas, sometimes crazy, sometimes good enough. One of them actually graduated, as you can see here, so it's not all pessimistic. And these two gentlemen who have started publishing are on their way, actually. Some people think that some of what we do is good science, so they decided to fund it, which is what which is where all of this actually comes from. So, as I said, I'm going to talk about the icing problem, and I'm going to try to throw in a little bit of a philosophical outlook that I personally have. And that has to do with, we are at a stage where energy is a major problem. And it has been like that for a very long time. And one of my pet themes is to think about energy efficiency. And if we are trying to solve some problems, let's say in this case a phase change problem, trying to come up with surfaces that can delay ice formation, meaning water freezing into its own solid phase, if you are trying to come up with a solution for that, wouldn't it be nice to be able to do that in as energy efficient manner as possible? Because that will have ramification all the way to the efficiency of the technologies that we are thinking about solving this problem for. So one way, and we can see from this example snapshots here, none of which are actually our own, we have lots of technologies that are influenced and affected by undesirable ice formation. So if we could come up with a surface that can significantly delay ice formation, we would be actually, at least partially, solving some of the energy problem as well. And that's precisely what I mean by so-called passive solution. Passive solution does not mean that we just sleep over, we don't worry about the problem, and it gets solved. It actually means we don't have to put in any active energy to sort the problem out. You know? This is hard stuff. And I have to confess, right at the onset, I am not going to be able to give you the actual solution. I will just show you some snapshot of what I think could be potential routes to solution. if I may. So for me, most of this actually started almost by accident. I am not a material scientist, but I was assigned a problem by my PhD advisor in University of Illinois to try to develop surfaces, to look at special surface properties which would be good to minimize drag. And at the time, we are thinking about 2007, 2008, there was big buzz about so-called super hydrophobic surfaces. What that means is what we see in nature quite a lot. So this is an example, a very celebrated example actually, of so-called lotus leaf. In the East, it has the reputation of being a symbol of purity, meaning that it actually grows in muddy water and dust cannot accumulate on lotus leaf. And the reason for that is its extreme hydrophobicity. Now, just to give you, let's say, a flat-out truth, of all the material that we have been able to synthesize as of today, if you take the most hydrophobic material that you can think of, Teflon, perfluorocarbon, and so on and so forth, and you make a smooth surface out of it, and you place a water droplet on top, and you try to measure the angle of the water droplet, which is what we call contact angle, you'll get a contact angle of about 130 degrees. This thing has a contact angle of 150 easy. Okay? Some of you who work on superhydrophobic surfaces, you know that we can easily make surfaces that can go up to 160, 170, and so on and so forth. 180 is a perfect sphere. How do they do that? Well, the way it happens is, if you look at the morphology of the lotus leaf here, it actually consists of some microscale bumps. And if you zoom in a little further, you'll see wax nanotubes, literally nanotubes. And nature has this. So what we are seeing is a hierarchical morphology that helps in hydrophobicity. And it helps to have wax, which is a hydrophobic material, to texture with. So what we are getting from here is, to make things extremely hydrophobic at least, we need to start with as hydrophobic a material as we possibly can, because we don't have a perfect material, and we start to roughen it. Okay, so we started with that, and we came up with some polymer composites, which we could simply spray coat. So basically, this was a hydrophobic polymer compatibilized with some acrylics, and we had some nanoparticles in it. We make a stable suspension. You spray it like you spray paint, and you can get a nanocomposite surface which is extremely super hydrophobic. This was done as part of my own PhD thesis. When I moved to ETH Zurich, my mentor, Professor Polikakos, said, well, you have been doing hydrophobicity for a while. Let's see if you can actually solve a problem. Let's look at ice phobicity. And because you are good at making super hydrophobic surface, let's see if we can use those surfaces to make ice phobic surfaces, with the naive idea that water and ice are basically the same molecule. So if we are good at making a surface resistant and hydrophobic, we will be making the surface ice phobic as well. I guess you will probably know the reason I use the word naive. It turns out that the very thing that makes the surface special for hydrophobicity, which is the roughness, is a killer when it comes to ice phobicity. If you start with any surface, make it rough, the probability of water freezing goes up. Regardless of temperature, you maintain your water at. So we are starting on a wrong foot in that sense. Okay? Let's see what else we have to worry about. So that brings me to the outline of what I want to tell you about. I'll start by giving you some brief overview of what I like to call icing physics. So far as I've been able to learn thermodynamics associated with phase change and ice formation. Then I'll get into so-called ice-phobic surfaces. And yes, I will try to get into some nanostructured surfaces, as my friend Renato wants to. Then I'll show you some results, and these are the new bits here, on drop impact tests I guess Juliana will see the reason I asked the question. And I'll try to summarize what we have been able to learn so far, and hopefully give you a sense of where I would like to take things further. And I would, of course, solicit your opinion on what you think about those ideas. So, how do we study icing physics? We have heard this time and again. This is my bad iPhone picture. So that's a jibe against Steve Jobs, not any of you guys. And I guess we recognize this happy fellow in the middle, all right? And this is a remarkable achievement. It suffices to say that if I had this facility available to me a few years back when I was getting started with ice-phobic surfaces, I wouldn't worry about developing the experimental setups that I have. So for those of the students who are lucky enough to start now, well, start working on this as fast as you possibly can, right? We didn't have this. So what did we do? Well, what we did is we built something that was about 20 times smaller than what you saw, okay? Which sort of looks like a mini icing wind tunnel. And the very basic premise that we wanted to start with was we wanted to see if these surfaces, these so-called superhydrophobic surfaces that we were making, were also so-called ice-phobic, or if they were able to delay ice formation, if you will. Very naive experiment. And this is literally outcome of first 10 experiments that the student who graduated actually performed. So this is what he started observing. So here's a video. So this is a droplet sitting on a superhydrophobic surface. And if we wait long enough, all of this is at minus 15 degrees centigrade in relatively dry humidity condition. If we wait long enough, what we see is we have nucleation down here at the interface between the droplet and the substrate. So this is heterogeneous nucleation. And this is not surprising. We would expect this to happen, because from basic thermodynamics, if we introduce an impurity into a cold liquid, we increase the possibility of nucleation on that impurity. In this particular case, that surface is impurity, if you will. So we would expect this, right? Now, this is the same experiment, except with a little bit of gas flow from the side. Literally 3 or 4 meters per second, so not too strong of a velocity at all. Yeah? Because if you have too strong of a velocity, this droplet will roll off before our experiments could actually finish. And what we see is the nucleation now seems to occur at the top. So we've got homogeneous nucleation. Now, so the first thing we started worrying about is, well, we have a bad mini wind tunnel. We don't have any control of the temperature, and probably that's why things are fluctuating. So we did whatever we possibly could in our little chamber to make sure that the substrate, water droplet, and the ambient temperature were as close as possible to minus 50. We still, whenever we would have airflow, we would have homogeneous nucleation. And what's happening here is something that we experience very much in a place like Rio in summer, especially when the humidity is high. When we sweat, we feel a little bit cooler. And the reason is the water droplet that comes out or forms on our body, it evaporates, and it takes the heat from our own body, and that makes us feel cooler. And that's exactly what is going on at the top here. Now, evaporation effect is not strong, especially if you keep the temperature between the surrounding and the evaporating droplet as close as possible. So here's a calculation, basic thermodynamic calculation of free energy for homogeneous nucleation and heterogeneous nucleation. Now, the energy barrier for homogeneous nucleation is typically above the heterogeneous one. Hence, we see heterogeneous nucleation most of the time. So if the temperature is maintained at any particular value, you will typically expect the one with minimum energy to prevail. So you would expect heterogeneous nucleation to prevail. And what's happening is, because of this evaporative cooling, we are introducing a little bit of cooling at the top. So now the top has an energy barrier that is down here, and the bottom is still up here. And so we start to see homogeneous nucleation. Now that's theorizing. If we had left this work at that point, we would not be able to publish anywhere, according to me. Here's the reason we managed to publish it. If we think that we've got ourselves a model, as simple as it is, we can play with the model. So one thing we can do is we can say, all right, let me start to change the contact angle of the surface. So I can start to change the material of my surface now. So here's a theoretical curve which has a contact angle of, let's say, 130. And why do I show you 130? If you look here carefully, this is very little cooling. But at 130, we start to see the heterogeneous nucleation one going well below even the evaporation limit for homogeneous nucleation. Meaning, below 130, we should start to see heterogeneous nucleation again. So probably when we have evaporative conditions, superhydrophobic surfaces are not the best to go. Can we prove this? And yes, exactly we did. So here's some experiments to show you exactly that. This is regular Teflon in dry humidity condition. We see, so contact angle is lower, we see heterogeneous nucleation. We go to 110, we still see heterogeneous nucleation. Let's go to the other side. Superhydrophobic surface again. Fairly high humidity, 75%. We see homogeneous nucleation. So high contact angle with evaporation is bad. It's giving you homogeneous nucleation. But if I make the environment saturated, 100% humidity, that means kill evaporation, I get back my heterogeneous nucleation. So this gives us the first good conclusion that evaporation during freezing is important. Yes? Why should we worry about it, other than the fact that we can publish a good paper? Here's why we should worry about it. So what I'm going to show you now is a video. I probably have shown this to people before. This is my absolute favorite video in whole of my research of about 40 research papers. Okay? Absolute favorite. And you'll see a reason in a second. So what I'm going to do is, what we're looking at here is 3 drops. 1, 2, 3. All maintained at minus 15 degrees centigrade. Eventually, if I give it enough time, they will freeze. What I do is I initiate this process. So I bring an ice crystal and I touch this guy. But I touch only him. This guy who is slightly apart from him, I don't do anything about. Okay? And let's see what happens. So I touch that, and you start to see flashes of evaporation actually. Right? So what's going on here? What's going on is, of course, because I see a lot of evaporation, why is, first of all, evaporation taking place when the freezing occurs? What happens is, when water freezes, it releases heat. Yes? That's why if we are in supercooled state, water is not in equilibrium. It doesn't like that state. It wants to release a lot of heat, get rid of that energy. Now, this thing is happening very fast. Right after I touch, entire droplet freezes. It releases a lot of heat. Where can that heat go? Well, if I have a thermally conducting substrate, let's say a metal surface, the heat could go through, because I'm doing this experiment in air, in stationary condition. So air is not the best route to go about, right? That's why we dress in layers. Okay. And if I do this experiment, in this case deliberately on an acrylic, which is thermal insulator, I make sure that the heat cannot go through the substrate either. So where is the heat going to go? It's going to be absorbed by any of the remaining liquid, which is going to evaporate at that point. But now think of this vapor. It comes out and it's in a minus 15 degrees centigrade climate. It cannot stay as vapor. So what does it do? It condenses down again. If you don't believe me, here. This is the part of the original droplet under the microscope, and this is a bright field developed around this original droplet. And you see condensate formation. Now some of this condensate touches the original droplet and forms a frozen ring around the original droplet. Now that frozen ring can touch the next guy, and so on and so forth. So, message here is, if we are trying to make ice-phobic surface, let's not make them insulators. 1. Message 2, it is bad to have evaporative condition. Dry humidity condition is not necessarily good for designing surfaces that are ice phobic. Because in this case, if one of these droplets freeze, it will lead to freezing of all the rest in an array, for instance. Yeah? So what did we do about that? Well, the first thing I'd like to do is to show you that this indeed is true, because this seems like a lot of hand-waving argument, right? So what I did is I solved a vapor diffusion equation around my droplet, and if you do it with respect to distance and time around, let's say, this original drop, you can actually very simply come up with, let's say, a humidity envelope, which shows that around your original droplet, there are going to be regions which are going to be greater than 100% in humidity, very close to it, but there are those regions. And away from it, there are going to be regions which are going to approach my environment, which is at lower humidity. This is the extent of so-called condensate ring, which is forming out of this original droplet. So these are experiments which show that I have a sudden condensate ring formation, and some of it actually can evaporate, giving me a final frozen ring that is somewhat extended from the original droplet here. And if I'm doing all of this correctly, I should be able to correlate that with the size of the so-called condensate droplets as well. What did we do for that? Indirect measurement. So we took these high-speed camera images, and we broke it down into three sectors, and we simply measured the brightness of these images, which more or less corresponds well to the size of the let's say, tiny condensate drops we are forming. And if we do that, what you see is at any location corresponding to this simple diffusion model-based prediction, I've got growth of my condensate drop, and then right about at this peak, it matures and then starts to come down and evaporate. What's the message of this? Other than the fact that this is a very complicated figure, I would like to emphasize the fact that freezing is not a single phase change problem. It's not just about water changing into ice. Depending on the humidity conditions you have, you may have evaporation, condensation, etc. going on at the same time. Life is a little more complicated than we think. Okay, so I promised you new results, so here's some new results that is brand new. So let's get into the actual topic, which has to do with nanostructured surfaces. Now, ETH does not have as nice wind tunnel as you guys have here. What we do have is a fairly good clean room. And we thought of making use of that, just to understand this problem ice formation a little bit better. So the first question we ask ourselves is, how do we design these ice-phobic surfaces, right? That's the number one question. Let's make it as hydrophobic as possible. Let's keep the roughness as low as possible. Let's try to make it thermal conductor. That's what we have learned so far. What else can we do? Well, we can borrow something from basic thermodynamics, which atmospheric science people know very much, actually. And that has to do with what is called the so-called Gibbs-Thomson relationship, which tells you that if you have water in a small pore, silica nanopore, for instance, a few nanometer in diameter, the freezing point will be depressed. It has to do with the simple fact that the ice nuclei are not able to form due to the confinement of the pore. Okay? That's a very simple way of putting it, but that's essentially at the heart of it. That also works. There are nature publications which show that some fish which have special proteins that make it very difficult for water to freeze on their surface and in their bloodstream have proteins that actually seem to make use of such confining pores. Okay? There it is confinement of these protein molecules. So we thought, all right, let's try to make surfaces that have texture and that have small pores on the surface, because then we will be able to exploit this over and above all of what we have learned so far. What can we do? So the first question was, what material to use? Silicon has a thermal conductivity of 150. That's not metal, but it's not bad either. There are metals which are lower than that. right? So we thought, let's start with silicon. The good thing about silicon is we can use it to process it in so-called microfabrication facility. And it turns out that if you take silicon and you coat it with a little bit of oxide, silicon oxide, and you put it in a machine called inductively coupled plasma, by simply tuning the time that you put this thing inside the inductive coupled plasma, you can tailor the roughness. And here's the precision to which you can tailor it. These are actual RMS numbers. So this is your smooth silicon wafer, below 1 nanometer in roughness. And we can actually go all the way up to 170 nanometers. So we're looking at approximately 3 orders of magnitude change in nanoscale roughness, yes? And use a little bit of leap of imagination, if you will, to see that these bumps here, they have small space in between them. So it's as though we have nano cavities on top of our surface. And we figured this is as good as any we can make in terms of a so-called ice-phobic surface that will exploit the Gibbs-Thomson relationship. Okay? And let's give that a shot. So we did our measurement, and we saw that on all these nanostructured surfaces, hydrophilic, hydrophobic, we have almost, for 3 order of magnitude change in the roughness, almost no change in so-called nucleation temperature. What is nucleation temperature? Well, I take the surface, I put it in my chamber, I put some water droplet on top, and I very slowly, in a quasi-static manner, cool the whole thing down, and I detect the temperature at which freezing takes place. And I do a box plot, 50 measurements, that means find out a spread and statistics. The red bars are the median, then we've got 25% above the median, 25% below, then we've got some whiskers here that are outliers and so on and so forth. It gives us a statistical sense of roughly the temperature at which ice should form on this surface, okay? All right, well, this is, I mean, it's not great. There is nothing exciting here, except for the fact that nucleation theory tells us that roughness should be very important in deciding the nucleation temperature. And what we see here is, well, it doesn't seem to have any role. So the first indication that I had was to tell the student, your experiments are wrong. That was the first indication. And he proved me wrong. Let's see if I can convince you of that too. How can we explain this? So the first thing we saw was, well, maybe we can think of the same melting point depression effect, which is the Gibbs-Thomson relationship. And if we make use of that, we see that at radius of curvature of about few nanometer, that's when this thing starts to make a difference. If we think in terms of nucleation theory for a specific value of contact angle, what we see is at very high radius of curvature, so almost like a flat surface, there is no difference. And at low radius of curvature, meaning for rough surfaces, things should become different, okay? That's what we expect from nucleation theory. Now, experiments have a mind of their own. They're saying that, no, there is no change. So for a while, we were worried about it, except there's one good thing to note here. This is not a bad thing. If we had all surfaces which were insensitive to roughness, this gives us a lot of flexibility in terms of using the so-called superhydrophobic surface that we gave up on in the beginning. So this may not be a bad way to go, actually. We still need to understand it. What is happening? So we looked at the literature, and in the literature, if there has been some excess cratering measurements, which show that, I'm not trying to modulate my voice. I have to tell you that, okay? It's just, this thing is very precise. So in the literature, there is this discussion that when ice forms on any surface, there is always this interface between an ice that is forming and the original substrate that we have. And what is that interface? Is it a sharp interface, first of all? Is it one molecule thing? If I go and ask this question to an undergraduate student, if I ask it in that manner, the response of an undergraduate student will be, no, it's not going to be a sharp interface, it's a real surface. And that's exactly what it is. In fact, what happens is, at the interface between ice and the solid substrate, there is something called a quasi-liquid layer. And this is shown by measurement after measurement, lots of nature and science papers. So we took a leap of faith. We said, well, what if, we haven't done anything special in designing our surfaces. What if the same quasi-liquid layer is also present in the ice crystals that are forming on our surface? So here's my nanocavity. This is an ice embryo that is forming, and I just assume that I've got a quasi-liquid layer. And all I do is basic undergraduate calculation of surface energy balance, and I come up with a dependence of this contact angle here of this ice embryo, which is dependent on the curvature of this nanocavity. This comes out naturally. You don't have to make any assumption for this, okay? And we said, okay, fine. If this were to be true, we can call this a confinement effect, and hopefully we can explain our results with that. Well, let's see if we can do that. This is where we were. If we use this so-called contact angle variation based on interface confinement, we come up with a theta variation that looks like this. So all we do is we go back to the same old nucleation theory, and we include this variation of contact angle in that. What do we get? Well, the reason I'm making the presentation is we get a perfect match. There is no fuzz of data here. There is absolutely no fuzz of data here. What we have done is we had the advantage of having a clean room, which gives us absolutely repeatable surface material, as close as we possibly can in experiments. I've shown you the spread in the data. And we have accounted for what is observed in other experiments on flat surfaces. That's all. Okay, so that was kind of nice and exciting. Can we do better? So we have forgotten about superhydrophobic surface, and I'm going to try to bring it back now gradually. Okay, so let's see if we can make use of that thing. Can we do better? Well, turns out yes, we can do better. What can we do? If we think in terms of nucleation rate, this is how the equation looks like, and up until this point I've tried to avoid equations as much as possible, but at this point I can't. So what we can do is we can look at this nucleation rate equation, which has surface area of contact between your liquid and the solid surface inbuilt into equation. So if you minimize the contact area between liquid and the solid surface, you minimize the probability of icing. If my liquid droplet was sitting on air, I will have least amount of possibility of nucleation, right? And that's exactly what we do. So what we do is we make our surface out of so-called micropillars, and on top of these micropillars, we inbuild some amount of nanotexture that we saw before, to get the dual benefit, the nanostructure benefit that we saw, and minimizing the surface contact. Does it work? Yes, it turns out it does work. So here's, let's say, a spread of data. I don't want to show you all the details of it. Let me just show you the difference that we were able to make with respect to the so-called nanostructured surface. So here's the nanostructured surface, and here's the hierarchical surface. And we see that we get a 2.5 degree reduction in the nucleation temperature due to this so-called hierarchical roughness, where I have now micropillars and on top nanostructured roughness. Now you will say, much ado about nothing, right? 2.5 degree, big deal. Why are you wasting our time? Your spread in data is that much. Wait a second. Let's look at this plot now, all right? So here, this is a different experiment, and the student almost hates me for this experiment, and you'll understand in a second why, okay? So here's the surface, let's say the best surface, and now I'm doing slightly different measurement. So I am now maintaining my drop and the substrate at a particular temperature, and I'm waiting till the drop freezes. So I am doing so-called freezing delay measurement, all right? So if I'm at nucleation temperature, I readily freeze. Now what is my nucleation temperature? Nucleation temperature is about -25 for the surface that we saw. Now I go by 1 degree higher. I go 1 degree higher, I start to get to about 10 to the power of 3 seconds. And if I go about a few degrees higher, I start to run into 10 to the 5 second, which is about a day, okay? And I must tell you that this line is the fit part, and these are actual experimental data. True. This is done in absolutely clean laboratory on a surface that is done in clean room environment. So this is not ready for daytime yet. But this is actually giving us some indication that we have some hope to be able to use some of these basic principles to design isophobic surface that can actually delay ice formation by a significant amount. A day is not very little. Day is not very little at minus 20 degrees centigrade. Okay? Do I have 10 more minutes or am I running too late? 5 minutes? Okay, I go 5 minutes and I'll finish. Okay, let me show you some results on drop impact. So this is experiments that we did very recently actually. We're talking now 6 months now. And we started with very simple and similar surface. The idea was to see if we can look at, let's say, micro and nanostructured surface, and if we can understand how, and if at all, we can predict impalement of water droplet on the surface. Because if a water droplet comes down and gets impaled onto my surface texture, it's not going to bounce off. That means I've got a bad surface to start with. If I want to use a super hydrophobic surface, I'd like to do what this guy was doing. It comes down and it takes off, right? So let's see if we can make use of that. So I want to make use of something like this. So the way we did this experiment is we designed a whole slew of surface, again, very regulated, and we tried to look at how the contact time of my droplet looks like. So how much time does my droplet spend on the surface during the impact event? And what we see is as we go down with the temperature, we have an increase in contact time. This is to be expected, because if I go down in temperature, my viscosity is increasing, right? So if the viscosity is increasing, the viscous dissipation is higher, so the droplet is bound to spend more time. No big deal, okay? And others have seen and proved this. What was interesting, at least to me, is these two numbers here. This is Weber number. Weber number is basically the ratio of inertia to surface tension. That's the simplest way to think about it. So we're looking at a velocity here, let's say, of about maybe less than a meters per second, and we're looking at a velocity of 2 meters per second. And if you look at two surfaces, let's say two microstructure surfaces, which have a diameter of pillar of about 5 micron and spacing of 9 micron in this case, and in this case 2.5 micron and 4.5 micron spacing, the beauty of these numbers is, if you look from the top, the solid fraction that the droplet sees is exactly the same. So meaning, if I put a droplet very gently, it sees the same amount of solid. I've just adjusted the diameter and the spacing, okay? Now, those two, they are overlapping here, okay? This black guy and the blue guy, they are overlapping here. Within the error of the measurement, there is no distinction between them. If I go to slightly higher Weber number, the droplet does come off, but here's the black fellow, and the blue one is hidden in here. So for me, the big question was, why is that happening? It's a subtle thing, why is that happening? Here's why it is happening. So what is happening is, if we just plot the diameter variation with time, we see that for both of these cases, we have almost no variation in this case at the low Weber number. At high Weber number, towards the end, these two curves start to look very, very different. And what's happening is, if you see at the center here, we start to see some pattern emerging. And what I think is happening is at the center, where the pressure peak appears, some of the liquid goes into these micropillars. And then the contact area changes. And when that changes, the contact time also changes. Now, that's the point where the failure occurs, because that's the point where the maximum pressure point occurs. What this is telling us is, if you are trying to make a surface that can also resist drop impact, make the pillars as fine as possible and make them as close as possible, so the liquid is not going to get in. Okay? So here's the sequence of what we see and the reason we were able to see that. And I'd like to just point you to, hopefully, if this guy plays. Oh yeah, it does. If you keep an eye on this guy here, you see a ring-like patch appearing. And if I can maybe pause this fellow. A little more. You should probably see that. Do you see this ring-like patch here? So what we see as a drop remaining here is actually a ring-like pressure peak, which is where the penetration is occurring. Okay? So if we are trying to make a surface that resists penetration, this is the zone that we have to worry about. And that's the reason the overall picture that is emerging looks like this. And this is my last slide. I'll finish after this. What we have is basically a drop. This is also known theoretically, actually. And the pressure peak, the calculations show, I didn't have time to get into that, is the pressure peak is a bifurcated peak. So you almost have a ring-like pressure peak, which is in agreement with the ring-like penetration that we are seeing from the top view. And the contribution that we made was, this was known, this was also known. We feel that there is an intermediate situation at intermediate Weber number when the physics is really interesting, and you start to see difference between how important it is to control the texture of the surface that you are making. Let's put it this way. Superhydrophobic surfaces are easy. You can do that in 10 minutes if you want to. If you really want to make a superhydrophobic surface and play with it, you can do that in 10 minutes. Ice-phobic surface, surprise, surprise, are very hard, are very, very hard. And hopefully I've been able to share some of my frustration regarding that. So this is an image of essentially an evaporation cloud around a droplet. So hopefully I have been able to share with you some of the fundamentals that we have learned in the last few years, and also some of the new results on drop impact. And the idea now would be to see if we can, based on what we have learned, this number here, this part here is important, push to higher speed. So ideally, I would like to not be confined at 4 or 5 meters per second that we are working at here. It will be great to have a surface that can resist 50 meters per second. And there are ways to get around to that problem too, I think. Then, ice adhesion is an important bit, okay? Between the frozen drop and the substrate, we could look at that, and maybe while we are at it, think about now designing surfaces that are going to be useful in real world. So do it in a scalable manner and not in clean room environment. The clean room part is done now. We've learned as much as we possibly probably could, so far as I can see at least. It's time to get to actual scalable nanostructuring. So with that, I'd like to thank you for listening and inviting me here. Absolute pleasure. Rio is a beautiful city. I would come here regardless because of the people, all right? Thank you very much for listening.